The World Geodetic System is a standard for use in cartography, geodesy, and navigation. It comprises a standard coordinate system for the Earth, a standard spheroidal reference surface for raw altitude data, and a gravitational equipotential surface that defines the nominal sea level. The latest revision is WGS 84, established in 1984 and last revised in 2004. Earlier schemes included WGS 72, WGS 66, and WGS 60. WGS 84 is the reference coordinate system used by the Global Positioning System. Main parameters: the coordinate origin of WGS 84 is meant to be located at the Earth's center of mass. The error is believed to be less than 2 cm. The WGS 84 meridian of zero longitude is the IERS reference meridian, 5.31 arcseconds or 102.5 meters east of the Greenwich meridian at the latitude of the Royal Observatory. The WGS 84 datum surface is an oblate spheroid with major radius equals 6,378,137 am at the equator and flattening f equals 1/298.2572235363. The polar semi-minor axis B then equals a times, or 6,356,752.3142 am. Currently, WGS 84 uses the EGM96 geoid, revised in 2004. This geoid defines the nominal sea level surface by means of a spherical harmonic series of degree 360. The deviations of the EGM96 geoid from the WGS 84 reference ellipsoid range from about a 105 am to about plus 85 am. EGM96 differs from the original WGS 84 geoid, referred to as EGM84. History: efforts to supplement the various national surveying systems began in the 19th century with F.R. Helmet's famous books Mathematische und Physikalische Theorien der Physikalischen Geodäsie. Austria and Germany founded the Zentralbau Quarter die Internationale Messung, and a series of global ellipsoids of the Earth were derived. A unified geodetic system for the whole world became essential in the 1950s for several reasons: international space science and the beginning of astronautics. The lack of intercontinental geodetic information. The inability of the large geodetic systems, such as European datum, North American datum, and Tokyo datum, to provide a worldwide geodatabases, need for global maps for navigation, aviation, and geography. Western Cold War preparedness necessitated a standardized, NATO-wide geospatial reference system, in accordance with the NATO Standardization Agreement. In the late 1950s, the United States Department of Defense, together with scientists of other institutions and countries, began to develop the needed world system to which geodetic data could be referred and compatibility established between the coordinates of widely separated sites of interest. Efforts of the U.S. Army, Navy and Air Force were combined, leading to the 2D World Geodetic System 1960. The term datum as used here refers to a smooth surface somewhat arbitrarily defined as zero elevation, consistent with a set of surveyors' measures of distances between various stations, and differences in elevation, all reduced to a grid of latitudes, longitudes, and elevations. Heritage surveying methods found elevation differences from a local horizontal determined by the spirit level, plumb line, or an equivalent device that depends on the local gravity field. As a result, the elevations in the data are referenced to the geoid, a surface that is not readily found using satellite geodesy. The latter observational method is more suitable for global mapping. Therefore, a motivation, and a substantial problem in the WGS and similar work is to patch together data that were not only made separately, for different regions, but to re-reference the elevations to an ellipsoid model rather than to the geoid. In accomplishing WGS A60, a combination of available surface gravity data, astrogeodetic data and results from HIRAN and Canadian shore surveys were used to define a best-fitting ellipsoid and an Earth-centered orientation for each of initially selected datum. The sole contribution of satellite data to the development of WGS A60 was a value for the ellipsoid flattening which was obtained from the nodal motion of a satellite. Prior to WGS 60, the U.S. Army and U.S. Air Force had each developed a world system by using different approaches to the gravimetric datum orientation method. To determine their gravimetric orientation parameters, the Air Force used the mean of the differences between the gravimetric and astrogeodetic deflections and geoid heights at specifically selected stations in the areas of the major datums. The Army performed an adjustment to minimize the difference between astrogeodetic and gravimetric geoids. By matching the relative astrogeodetic geoids of the selected datums with an Earth-centered gravimetric geoid, the selected datums were reduced to an Earth-centered orientation. Since the Army and Air Force systems agreed remarkably well for the NAD, ED and TD areas, they were consolidated and became WGS 60. The United States Department of Defense World Geodetic System 1966, steps to the improvement of a global system were the astrogeoid of Irene Fisher and the astronautic Mercury datum. In January 1966, a World Geodetic System committee composed of representatives from the United States Army, Navy and Air Force, was charged with the responsibility of developing an improved WGS needed to satisfy mapping, charting and geodetic requirements. Additional surface gravity observations, results from the extension of triangulation and trilateration networks, and large amounts of Doppler and optical satellite data had become available since the development of WGS 60. Using the additional data and improved techniques, WGS 66 was produced, which served 2D needs for about 5 years after its implementation in 1967. The defining parameters of the WGS 66 ellipsoid were the flattening, determined from satellite data, and the semi-modular axis, determined from a combination of Doppler satellite and astrogeodetic data. A worldwide 5-degree mean free air gravity anomaly field provided the basic data for producing the WGS 66 gravimetric geoid. Also, a geoid reference to the WGS 66 ellipsoid was derived from available astrogeodetic data to provide a detailed representation of limited land areas. The United States Department of Defense World Geodetic System 1972, after an extensive effort extending over a period of approximately 3 years, the Department of Defense World Geodetic System 1972 was completed. Selected satellite, surface gravity and astrogeodetic data available through 1972 from both 2D and non-2D sources were used in a unified Wgs solution. The results of the adjustment consisted of corrections to initial station coordinates and coefficients of the gravitational field. The largest collection of data ever used for WGS purposes was assembled, processed and applied in the development of WGS 72. Both optical and electronic satellite data were used. The electronic satellite data consisted, in part, of Doppler data provided by the U.S. Navy and cooperating non-2D satellite tracking stations established in support of the Navy's navigational satellite system. Doppler data was also available from the numerous sites established by geodesies during 1971 and 1972. Doppler data was the primary data source for WGS 72. Additional electronic satellite data was provided by the SECO or Equatorial Network completed by the U.S. Army in 1970. Optical satellite data from the Worldwide Geometric Satellite Triangulation Program was provided by the BC-4 camera system. Data from the Smithsonian Astrophysical Observatory was also used, which included camera and some laser ranging. The surface gravity field used in the unified WGS solution consisted of a set of 410 10-degree equal area mean free air gravity anomalies determined solely from terrestrial data. This gravity field includes mean anomaly values compiled directly from observed gravity data wherever the latter was available in sufficient quantity. The value for areas of sparse or no observational data were developed from geophysically compatible gravity approximations using gravity geophysical correlation techniques. Approximately 45% of the 410 mean free air gravity anomaly values were determined directly from observed gravity data. The astrogeodetic data in its basic form consists of deflection of the vertical components referred to the various national geodetic datums. These deflection values were integrated into astrogeodetic geoid charts referred to these national datums. The geoid heights contributed to the unified Wgs solution by providing additional and more detailed data for land areas. Conventional ground survey data was included in the solution to enforce a consistent adjustment of the coordinates of neighboring observation sites of the BC4, SECOR, Doppler and Baker-Nunn systems. Also, 8 geodiameter longline precise traverses were included for the purpose of controlling the scale of the solution. The unified Wgs solution, as stated above, was a solution for geodetic positions and associated parameters of the gravitational field based on an optimum combination of available data. The Wgs 72 ellipsoid parameters, datum shifts and other associated constants were derived separately. For the unified solution, a normal equation matrix was formed based on each of the mentioned data sets. Then, the individual normal equation matrices were combined and the resultant matrix solved to obtain the positions and the parameters. The value for the semi-modular axis of the Wgs 72 ellipsoid is 6A378 A135 meters. The adoption of an A value 10 meters smaller than that for the Wgs 66 ellipsoid was based on several calculations and indicators including a combination of satellite and surface gravity data for position and gravitational field determinations. Sets of satellite-derived station coordinates and gravimetric deflection of the vertical and geoid height data were used to determine local to geocentric datum shifts, datum rotation parameters, a datum scale parameter and a value for the semi-modular axis of the Wgs ellipsoid. 8 solutions were made with the various sets of input data, both from an investigative point of view and also because of the limited number of unknowns which could be solved for in any individual solution due to computer limitations. Selected Doppler satellite tracking and astrogeodetic datum orientation stations were included in the various solutions. Based on these results and other related studies accomplished by the committee, an A value of 6A378 A135 meters and a flattening of 1/298.26 were adopted. In the development of local to Wgs 72 datum shifts, results from different geodetic disciplines were investigated, analyzed and compared. Those shifts adopted were based primarily on a large number of Dopplertranet and geodesy station coordinates which were available worldwide. These coordinates had been determined using the Doppler point positioning method. A new World Geodetic System, WGS 84. In the early 1980s the need for a new World Geodetic System was generally recognized by the geodetic community, also within the U.S. Department of Defense. WGS 72 no longer provided sufficient data, information, geographic coverage, or product accuracy for all in current and anticipated applications. The means for producing a new WGS were available in the form of improved data, increased data coverage, new data types and improved techniques. GRS-80 parameters together with available Doppler, satellite laser ranging and very long baseline interferometry observations constituted significant new information. An outstanding new source of data had become available from satellite radar altimetry. Also available was an advanced least squares method called collocation which allowed for a consistent combination solution from different types of measurements all relative to the Earth's gravity field, that is geoid, gravity anomalies, deflections, dynamic Doppler, etc. The new World Geodetic System was called WGS 84. It is currently the reference system being used by the Global Positioning System. It is geocentric and globally consistent with an A ± 1 AM. Current geodetic realizations of the Geocentric Reference System family International Terrestrial Reference System maintained by the IERS are geocentric, and internally consistent, at the few cm level, while still being meter-level consistent with WGS 84. The WGS 84 originally used the GRS-80 reference ellipsoid, but has undergone some minor refinements in later editions since its initial publication. Most of these refinements are important for high-precision orbital calculations for satellites but have little practical effect on typical topographical uses. The following table lists the primary ellipsoid parameters. The very small difference in the flattening thus results in a tiny difference of 0.105 mm in the semipolar axis. Longitudes on WGS-84. WGS-84 uses the IERS reference meridian as defined by the Bureau International de l'Heure, which was defined by compilation of star observations in different countries. The mean of this data caused a shift of about 100 meters east away from the prime meridian at Greenwich, UK. The longitude positions on WGS-84 agree with those on the older North American datum 1927 at roughly 85° longitude west, in the east-central United States. Updates and new standards. The latest major revision of WGS-84 is also referred to as Earth Gravitational Model 1996, first published in 1996, with revisions as recent as 2004. This model has the same reference ellipsoid as WGS-84, but has a higher fidelity geoid. Many of the original authors of WGS-84 contributed to a new higher fidelity model, called EGM 2008. This new model will have a geoid with a resolution approaching 10 km, requiring over 4.6 million terms in the spherical expansion. See also, GPS, Transit System, $83 Namibian, ETRS 89, EGM 96, Geo, for marking up WGS 84 coordinates in HTML, Degree Confluence Project, Geotagging, Point of Interest, Geodetic System, References. External links, Geodesy for the Layman, Chapter 8, The World Geodetic System, NIMA Technical Report Trail 8350.2 Department of Defense World Geodetic System 1984, Its Definition and Relationships with Local Geodetic Systems, 3rd edition, National Geospatial Intelligence Agency. This is the official publication of the standard, including addenda. Note this report actually documents the EGM 96 model. The original WGS-84 is documented in versions prior to 1996. Main NGA page on Earth Gravity Models, Technical Manual DMATM 8358.1, Datums, Ellipsoids, Grids, and Grid Reference Systems at the National Geospatial Intelligence Agency. Description of the difference between the geoid and the ellipsoid from the US NOAA National Geodetic Survey GEOID page, NASA GSFC Earth Gravity page. Geographic Lib provides a utility geoid to evaluate the geoid height for the EGM-84, EGM-96, and EGM-2008 Earth gravity models. Here is an online version of geoid. Spatial Reference EPSG Projection 4326, WGS-84. This article incorporates a public domain material from websites or documents of the National Geodetic Survey.